Okay, so we are going to discuss translations of our field. Okay. Um, Now you have discussed translations of wave functions before, and you discussed translations in time. That was just normal quantum mechanics. So I want to remind you of some of that discussion and introduce something that you may have seen, maybe you didn't see, but that's okay if you didn't see it. We'll develop it now. So the version of quantum mechanics that you will have seen is called the Schrödinger picture. So this is what I would like to develop now. And you might not have seen it. And if not, that'll be fine. We're going to use another version of quantum mechanics called the Heisenberg picture. So let's start off developing these two. Okay. In the Schrödinger picture, perhaps the most important equation is the Schrödinger equation. And the Schrödinger equation tells us that I'm going to put h bar in for now, h bar d by dt psi is equal to h psi. So this tells us the dynamics of the system. Let's make a simplifying assumption that the Hamiltonian is time independent. Now, if the Hamiltonian is time independent, then I'm sure you know the solution. So let me just write it down. Psi of t would be, psi of t would be e to the minus I ht. If we put h bar in, that's where h bar would go, times by psi of naught. So let's just discuss this a little bit. Well, the Schrödinger equation is a first order differential equation. So to solve that, I have to integrate once. Whenever I integrate, there is a constant of integration. And the constant of integration is set by the initial condition. So this kept psi of naught, that is set. That's the arbitrary constant of integration. Psi of t is a solution no matter what psi of naught is. So this arbitrary constant of integration psi of naught must be fixed by stating what the initial condition is. So that's the first thing, okay? What is this equation telling me? It's telling me that if I've got the state psi of naught, then if I want to translate it forwards in time to the time t, I can do that with the operator e to the minus I ht over h bar. So there's an operator that translates states forward in time. This translation rule is the rule telling you how to translate a ket forward in time. But we might also ask, well, how do we translate a bra forward in time? And how do you get the rule for the bra? Well, you dagger the equation that you've got. So if I dagger ket psi, I will get bra psi. So there's bra psi is equal to. And when I dagger the operator and the ket, they will swap order and become a bra and a ket. So I will get bra psi of naught. Then I'll again have my exponential. Now, when I take the dagger, I need to complex conjugate any number. So minus I will turn into plus I. I need to dagger the Hamiltonian. That's an operator. But we know the Hamiltonian is Hermitian. So we know that H is equal to H dagger. So I'll just get H there because H is equal to H dagger. And I need to complex conjugate T, but T is a real number. And then I again need to divide by H bar. So there is the H bar sitting inside there. H bar is real. So complex conjugate of H bar still H bar. So actually, this equation tells me how to translate the bra, psi of naught, forwards in time. I also do it by an operator, but notice now I would use the operator e to the iht over h bar. So I would use a different operator. Okay, so states evolve in time in the Schrödinger picture. So states evolve in time. So you change time and your state will change. We also have operators. Our observables are operators. And we could have things like x, the position operator. We could have the momentum operator. And in the Schrödinger picture, operators don't evolve. Okay, so x of t was equal to x of naught, and p of t is equal to p of naught. This is in the Schrödinger picture. This shouldn't be very surprising to you. I think that you're probably used to the fact that in position space, the momentum operator becomes minus I h bar d by dx. And you use that rule, and you might have asked yourself, at what time is that rule hold? Well, you use that rule for all times. There wasn't some specific time range at which you couldn't use that rule. You always use that rule, okay? If we're in quantum mechanics, what are the things that we would measure? Well, every time we want to measure something, it takes this form. We've got some bra, let's call it phi of t. We've got some operator, let's call it O, and then we've got some ket, psi of t. Now, you might want to calculate what is the transition, the probability that you make a transition from an initial state to a final state. Then you would have an overlap of a bra and a ket without an operator sitting in the middle. Well, that's also an example of a formula like this, just that O is the identity. But you might also be calculating, for example, the shift of an energy level. And the shift of an energy level would involve things like a state, an operator, a state. You could be calculating the expectation value of some observable. And then you have bra state, some operator, ket state. So all of the physical things that you might want to calculate in quantum mechanics all take the form of this matrix element that I've shown you over here. So if you have two different ways of doing a calculation, but they give you the same answer for this matrix element, you would be absolutely certain that these two different ways of doing the calculation will agree on all possible physical predictions that you could make. Okay. Now, I'd like to write down what is this quantity. So what I'm going to do is, for the bra, I'm going to use the known time evolution of the bra, okay? In fact, I think I'm going to run out of space, so let me try to help myself. So I'm going to put, this is equal to, I'm going to put the bra at time naught. Then I've got e to the I ht. I'm not going to write the h bars anymore, okay? So this quantity that I've written, this quantity, this is just 5t. Then I am going to write in my operator O. So that's fine. And then I'm going to write in psi of t. Well, take a look again at the time evolution. Psi of t would be e to the minus I h t. Again, I'm not going to bother about h bar. You can put them in if you want. And psi of naught. So just to make things completely explicit, that bit over there is for that over there. Okay. So I hope you can see how I've gotten this formula. And in fact, let me even modify this slightly. So in the Schrödinger picture, we said the operators don't evolve. So let's imagine this was the O at time t, and O at time t will be equal to O at time naught. Okay, so let me put here O at naught. Okay, good. So I have expressed this physical quantity, this matrix element, in terms of quantities all expressed at time t is equal to naught. Now I want to start developing the Heisenberg picture. In the Heisenberg picture, we will find that states do not evolve in time, but that operators do evolve in time. So it's the exact opposite of Schrödinger picture. In Schrödinger picture, the states evolve, but the operators don't. In Heisenberg picture, the operators evolve and the states don't. We'll continue in a moment.